The first test of surface tension and intermolecular forces looked at a liquid which is swirled, creating a vortex in which the surface level of the center of the liquid is substantially below the surface level of the perimeter. The time it takes for the vortex to disappear when the flasks are swirled with the same intensity and same duration were timed. The three liquids we used were glycerol, water, and isopropyl alcohol, but the flasks were labeled A, B, and C, which means we did not know which liquid corresponded to a set flask. Throughout the experiment, we found that when we timed the duration of the vortex of each substance, substance A's vortex lasted for 5.26 seconds, while substance B's vortex lasted for 7.36 seconds, and finally, substance C's vortex lasted for 1 second. To determine which liquid corresponded to which flask, we look at the intermolecular forces and bonds. If we look at the structure for isopropyl alcohol, water, and glycerol, we can see that glycerol has the most hydrogen bonds with 3 sites, while water has 2 sites, and isopropyl alcohol has 1 site. Now keep in mind, the stronger a molecule's intermolecular forces, the stronger its surface tension, which results in a longer time for the vortex to disappear because of the nature of vortex formations. When we swirl the flasks, we are essentially breaking the bonds, and as the vortex is forming, the liquid is then creating new bonds. So, to stop the vortex, the bonds have to again be broken, which means that the stronger the intermolecular force is, the longer the vortex will last. But from this, we can easily assume that liquid A would be water, liquid B would be glycerol, and liquid C would be isopropyl alcohol, because liquid B has the longest duration, meaning it could correlate to glycerol. Liquid A would have the second longest duration, meaning it can correlate to water, and liquid C, having the least duration, could be identified as isopropyl alcohol. But this is not the case. The intermolecular forces in glycerol are so strong that the swirling motion is not strong enough to actually break the bonds long enough for the vortex to form. This means that liquid C has to be glycerol, liquid B has to be water, and liquid C has to be isopropyl alcohol. Again, because glycerol's intermolecular forces could not be broken by the swirling motion, but since water could, and so could isopropyl alcohol, waters would have the longest duration, while isopropyl alcohol would have the second longest. The second test of surface tension and intermolecular forces had to do with looking at the effect surface tension had on a liquid based on the droplet shape it conceded when 5 drops of each liquid, isopropyl alcohol, water, and glycerol, were dropped onto a petri dish using a pipette. Once we performed this experiment using the same 3 unknown liquids from the previous test, we found these as our results. As you can see, liquid A has a very large surface area. It dispersed very thinly, and there was no noticeable hump. Meanwhile, liquid B did form a bead shape due to its greatly reduced surface area for the same volume, and there was an observable hump formed. Lastly, liquid C took up the least surface area, resulting in a very circular shape with the largest observable hump. To match these results with the specific liquids, we have to go back and look at surface tension. Now, surface tension is the tension of the surface film of a liquid caused by the traction of particles in the surface layer, which tends to minimize surface area. So simply put, the higher the intermolecular forces, the larger the surface tension, resulting in a more minimized and compact surface area for the same volume. Now, if we look back at the structure of the 3 liquids, glycerol, water, and isopropyl alcohol, we again notice that glycerol has the most sites for hydrogen bonds, making it the strongest in terms of intermolecular forces, followed by water and finally isopropyl alcohol. This means glycerol will have the highest surface tension, followed by water and isopropyl alcohol, meaning liquid A corresponds to isopropyl alcohol, liquid B corresponds to water, and liquid C corresponds to glycerol, just as shown in our first test. In this experiment, temperature change between the initial temperature of water and the temperature change as ethanol is added and as glycerol is added to water is calculated and compared. Through experimentation, we found that cup A, which is for water and ethanol, had water starting off at an initial temperature of 23.6 degrees Celsius. And after mixing ethanol into that water, the final temperature plateaued at 29.3 degrees Celsius, resulting in a temperature change of 5.7 degrees Celsius. Cup B, on the other hand, was for water and glycerol, which had water start off at an initial of 23.5 degrees Celsius. And after mixing that water with the glycerol, the final temperature plateaued at 25 degrees Celsius, creating a temperature change of 1.5 degrees Celsius. To find out why this occurred, the structure of both ethanol and glycerol must be observed. Of the two, ethanol only has one site for H bonds, while glycerol has three sites for H bonds. But ethanol is an overall smaller molecule compared to that of glycerol, as ethanol only has two carbons, while glycerol has one, two, and three carbons, resulting in ethanol to have less sites for LDF to occur, making it require less energy to break its bonds before dissolving in water. Glycerol, on the other hand, is a larger molecule with more LDF sites, requiring it to use more energy to break bonds to dissociate. So overall, the stronger the intermolecular force is, the more energy is required to break bonds. Now keep in mind, breaking a bond absorbs energy while making a bond releases it. Since it is easier to break ethanol's bonds, when they are remade, they release more energy. And since more energy is required to break glycerol, less energy is released when bonds are remade. In this experiment, the temperature change between the three alcohols methanol, isopropyl alcohol, and pentanol were observed and compared as they evaporate off the temperature sensor. We found that the temperature for pentanol over 50 seconds started off at 25.5 degrees Celsius and reached 24.5 degrees Celsius, resulting in an average evaporation rate of negative 0.02 degrees Celsius per second. For methanol, we found that over 50 seconds, the temperature changed from 25.5 degrees Celsius to 17 degrees Celsius, resulting in an average evaporation rate of negative 0.17 degrees Celsius per second. And finally, for ethanol, we found that over 50 seconds, the temperature changed from 22.8 degrees Celsius to 17.5 degrees Celsius, resulting in an average evaporation rate of negative 0.106 degrees Celsius per second. Now, if we were to actually look into the structure of the alcohols, ethanol, methanol, and pentanol, the results would make sense. The structure of methanol is the smallest of the three, with the smallest molar mass at 32.04 grams per mole. And since it only has one carbon and one hydrogen bond, the same amount of hydrogen bonds as all the other three alcohols, again, it will have the least surface area and the least sites for LDF to occur. Therefore, methanol requires the least energy to overcome the intermolecular forces, resulting in the fastest evaporation rate, which is exactly what we got here. For pentanol, on the other hand, this is the largest molecule with the largest molar mass of the three at 88.15 grams per mole with 5 carbons and 1 OH bond. which again is the same number of OH bonds as all three of the alcohols. This results in pentanol to have the largest surface area and the most sites for LDF to occur of the three. Therefore, pentanol will require the most energy to overcome the intermolecular forces, resulting in the slowest evaporation rate of the three alcohols, which again is exactly what we got. Now finally, for ethanol, it is in between methanol and pentanol in terms of average evaporation rate due to its molar mass being in between pentanol and methanol at 46.07 grams per mole, as well as other factors like it having 2 carbons and 1 hydrogen bond, again, like all the other three, results in a molecule with more surface area and sites for LDF compared to pentanol, but less surface area and less sites for LDF compared to pentanol.